Hello, everyone. Welcome to today's lecture on Introduction to Big O Notation, Space and Time Complexity. So, Big O notation is an essential concept in computer science. It helps us analyze and understand the efficiency of algorithms. So, by the end of this lecture, you're going to have a good grasp of how to evaluate both time and space complexity for algorithms and understand why these metrics are so important in writing scalable and efficient code. What is Big O notation? So, Big O notation is a way to describe the performance of an algorithm in terms of its growth as the input size increases. So it focuses on the upper bound of an algorithm's runtime or memory usage, which means we're primarily interested in the worst case scenario. So why do we care about Big O? It's because it allows us to abstract away hardware specifics like CPU speed or memory limits because they can change always and instead focus on how the algorithm behaves as the size of the input, often denoted by n. And this helps us compare algorithms and choose the best one for our needs. Why is Big O important? So why should we care about Big O? Say you're working on a system that processes millions of data points. If your algorithm doesn't scale well, it could slow to a crawl or even crash as the data grows. So Big O gives us the tools to predict and optimize performance, ensuring we use time and memory efficiently. Choosing the right algorithm can mean the difference between a program that completes in seconds and one that takes hours. This makes Big O crucial for developers, data scientists, or anyone building software for real world problems. Time complexity. So let's talk about time complexity. Time complexity measures how the execution time of an algorithm increases as the input size grows. So, for example, accessing an element in an array takes the same time no matter how large the array is. So this is O1. Or, but if you have to search through the entire array, that takes of n or linear time, where n is the number of elements in the array, and sorting the array often fall under n log n, and poorly optimized algorithms like bubble sort can have a time complexity of n squared. So understanding time complexity helps you predict how an algorithm will perform as input size grows. Space complexity. So we have space complexity. It is very similar to time complexity, but space complexity measures how much memory an algorithm uses. Space in complexity includes two parts, fixed memory like variables and constants, and variable memory like dynamically allocated structures or recursive calls. For example, an iterative algorithm that simply scans an array might use O1 space because it doesn't have to allocate extra memory. On the other hand, a recursive algorithm like the Fibonacci sequence might use of n space due to the call stack. So understanding space complexity is key when memory is a limited resource. Common time complexities. Here are some common time complexities, starting with O1, our constant time, where the algorithm's runtime doesn't change with the input size. Next is log n. You will often see in algorithms like binary search, which divide the problem space in half at each step. Then we have O of n, or linear time, for tasks like scanning through an array. More complex operations like sorting can range from n log n for merge sort to n square for bubble sort. Finally, there are exponential and factorial complexities. Exponential complexity being 2 to the nth power, and factorial being n factorial. And they can be impact practical for large inputs due to their rapid growth in time complexity. How to analyze time complexity? In order to determine the time complexity of an algorithm, you can generally follow these steps. First, you want to identify the basic operations like comparisons or assignments. Next, you want to count how many times these operations are executed relative to the input size n. Finally, you want to simplify by dropping lower order terms and coefficients, as these become negligible for large n. So, for example, a single loop iterating over n elements has O of n complexity, while nested loops result in n square. So, by analyzing your code this way, you can evaluate its efficiency objectively. Space complexity breakdown. So let's break down space complexity further. Fixed memory refers to constants and variables, which remain the same regardless of the input size. Variable memory, however, depends on the data structures or recursive calls used in the algorithms. For example, sorting an array iteratively requires no extra space, giving it a one space complexity. In contrast, recursive solutions often require extra space for the call stack. So when designing algorithms, you want to consider whether you can reduce space usage without sacrificing clarity or performance. Visualizing growth rate. We looked at this graph, but let's look at this again because this graph really illustrates how algorithms with different complexities grow as the input size increases. If you see O1, O1 remains flat while log n grows very slowly, and linear algorithm O n, you can see that it scales predictably as n increases. But when you have quadratic algorithms such as n square, it scales much faster than linear algorithms, and beyond to the nth power or n factorial, they grow much faster. So you want to notice how even small differences in complexity can lead to significant performance differences as n increases. So this is the reason why reducing complexity even slightly can have a huge impact for large inputs. Space-time trade-offs. So optimizing algorithms often involves a trade-off between time and space. Recursive algorithms might save time but use more memory for the call stack. And iterative algorithms might save memory but could be slower. So for example, quicksort is faster on average, but may require extra space for recursion, while iterative sorting algorithms save space but may not perform as well. So, understanding the problem constraints helps you decide the right balance between time and space. Practical applications. So, in practice, the choice of algorithm depends on the problem and constraints. So, for example, say you're searching a list. A linear search works for small inputs, but binary search is far more efficient for larger sorted lists. Similarly, sorting small datasets might work fine with bubble sort, but for larger datasets, quick sort or merge sort might be preferable. So the key is to match the algorithm to the input size and resource limitations for optimal performance. Conclusion to wrap up. So Big O notation is a powerful tool for evaluating algorithm performance, and time complexity measures how fast an algorithm runs, while space complexity evaluates its memory usage. So both are crucial for designing scalable, efficient solutions. By understanding these concepts, you will be much more ready to write code that performs well under real world constraints. Thank you everyone for listening.